call that? What did we say? Well, it says it. When a distance time graph is horizontal, we know that the object's not moving, yes? So the object's stationary. Now, when it comes to, what was it? Speed, yes?
Where are we?
And so, that was distance time. So you have to be careful because these graphs here look very similar, but their vertical axis here is labelled velocity or speed. Okay? So you've got to be careful when you're looking at these kinds of graphs for which information you have been given. So these compare speed or velocity and time. So time will always be on horizontal. Okay? On a speed time graph, a horizontal line would indicate that the object was travelling at a constant speed. Okay? So here, if this is flat, it means that this part here is at constant speed.
Oh, it doesn't mean it's stationary?
Correct. Okay, and so that's why I wanted to make sure you're clear between the difference between having distance in time to velocity in time. I would hope it would also make sense, but the trouble is, as soon as you're in a test situation, often common sense seems to go out the window. Because if this is talking about the speed of an object, then we're saying that we're talking about just this horizontal portion. We're saying that the time is moving on, but what's happening to the speed? It's at the same value, which means it hasn't increased or decreased. Yes? So it's still travelling at the same speed, but it's the same speed. Whereas if we were talking about distance ones, if we were talking about a horizontal portion here, our time is ticking along, but our distance hadn't increased at all. Therefore, that's why that indicates stationary.
On the speed time graph, if it was that, it was horizontal, but the speed was at 0.
Yes, fair enough. But you wouldn't often have that. Okay? Yeah?
Is it only stops when it comes down to the axle?
No, so now I'm going to talk about the slanty bits. Now, the slanty bits, this indicates that as time is increasing, our speed is doing what? Increasing. So when your speed is increasing, do we know what that talks about?
Acceleration.
Acceleration, yes. So that means that our object is accelerating. Yes? Are we all happy with that? So when you have a line like this, it means it's accelerating.
And then decelerating.
And this, yes, would be decelerating. Thanks for the notes. Right, so as it says here, the graph tells about the acceleration of the object rather than the speed. So here are some helps for you. You're almost so just sit down, look. So straight lines talk about that we've got constant acceleration. Okay, so these are straight lines. They don't mean horizontal, any straight line. The gradient of a line indicates the acceleration. So we know gradient is rise over run. Yes? The steeper the gradient, the higher the acceleration. So if it's up steep, it means it's going increasing really quickly, which means accelerating a lot. Positive gradient, it's increasing. Negative, it means it's decreasing. And horizontal lines means no acceleration, therefore it's got a constant velocity. Alright, so they are the things that you want to remember when it comes to speed graphs. So here we go. Velocity time graph below shows some information about a cyclist's journey. Describe what is happening during each of the paths AB, BC, CD on the graph. So AB, what's happening at AB? It's accelerating.
It accelerates to
I don't know what I said. Accelerating. I don't know how much information they're requiring here. I should have double checked, but I think acceleration will probably be enough, so we need to write it down somewhere. It says it here. Oh, yeah. God love me.
I wrote it anyway.
Oh, well, you're just awesome.
What are you reading?
BC. So BC, it's a horizontal line. So what did we say about horizontal lines? Constant velocity or constant speed, yeah. Now you already read the answers. And then C to D is decelerated.
I accelerated.
Good girl. You're one.
Well, yeah, I knew it, but like, I didn't read it.
I thought you actually said that you knew it from business. Well, why are you doing business? Alright, so B, work out the cyclist. Oh my god, what's wrong with me? The cyclist's acceleration during the first 10 seconds. So if we're trying to find our acceleration, how do we say we find acceleration? The gradient? The gradient, because yeah. So rise and run. So our rise would be 12, and our run would be 2. But is it the first 10 seconds? Yes. Why is it 6 o'clock? You're counting squares. No, darling. Alright, so always when we're finding gradients, and this goes back to normal straight lines as well, Emma, when you're finding gradients, you must always look at the scale of the axes. Alright?
Okay.
That's what caused some people to make mistakes in the test as well. So I guess I've got the answer here as well. Yeah. So first 10 seconds C goes from 0 to 12, so it's 1.2. Now notice here, your unit for acceleration is meters per second squared. Okay, so that's what this means. ms minus 2 means meters per second squared. Write down the highest velocity that the cyclist achieves during his journey.
No.
The highest velocity would totally be 12. Work out the distance travelled. Now, distance travelled is indicated by the area under the graph. Okay, so that's also something that we want to be aware. So while he's travelling at his highest velocity, is up here, yes? And that would be the area under the graph. How do we find the area of that bad boy? Well, we need to know this measurement. And what is this measurement? 50. Trisbians. And what's this measurement? 12. So we're going to do 12 multiplied by 15, which is 180 apparently. Trisbians?
Wouldn't it? No, you know, like, when you
I'm sorry, Kelly?
the area under the graph, in the holes in the graph, couldn't say
Oh.
the line.
I apologise. The area under the graph, but they're talking about when he's travelling at his highest velocity. So if they want to know the total distance that he's travelled full stop, then you would find this area and add the whole thing together. But they want specifically the distance he's travelled while he is travelling at his highest velocity. So that's why we're only finding this area.
Why is it as
This is just the unit for acceleration. So it means meters per second squared.
Can you find it differently?
Do you remember? You could probably just get away with writing that. The reason we've done index laws, haven't we?
No, but we
Have we done this yet?
No.
What? We have like power rules.
Oh, no, we lost.
Okay. So this line here indicates it's a division, yes? So we've got meters divided by a second squared. Does anyone remember anything about powers when they are on the bottom of a fraction? They would be, if they were moved up to the top, they would become negative. So that's why it's ms to the negative 2.
That would be positive.
Huh?
Why you just do M2 over S?
Because that's not what that means. It means meters per second squared, not the meters per squared, just the second. Because the meters was on the top to start with. And we're going into a whole complete, oh, no, I didn't see that. We're going into a whole lesson here. So if I had 7 over x power 4, I could rewrite that as 7x to the negative 4.
Really?
Because this here, being underneath the fraction, can be written like this next to it. I mean, this is a whole different lesson.
It's just like a thing.
And if you had just 8 over x, this has got a secret power 1. So that's 8x to the negative 1. That's why the speed is meters per second can also be written as that.
Wow.
Okay?
Wow.
There was side information. Oh,